James, over to you.
Okay, so thanks for the introduction. I'd like to thank Polly for inviting me to talk today on my research using the ACRC HPC facilities. And I'm going to present today some results of a combined experimental and simulation, first principles molecular dynamics simulation study of the atomic scale structure of liquid gallium under high pressure conditions. And the experimental part was done at Diamond Light Source, which is the UK's national synchrotron radiation facility, and around complementary ab initio molecular dynamics simulations on Blue Crystal 4. So the work I'm going to present today is a subject of a recent paper entitled Structural Ordering in Liquid Gallium Under Extreme Conditions, and this was published in Physical Review Letters in April, so during lockdown. And it's available open access, so please take a look. And I take the opportunity now to acknowledge my co-authors, Francesco Turchi, who's from physics and did much of the structural analysis of the simulation trajectories, and Benedict Heinen, Faye Quinn, and Oliver Lord, my colleagues in Earth Science, who together with Simon McLeod and Annette Klebb assisted with the synchrotron measurements. So why did I choose to look at gallium and liquid gallium? And so gallium's a remarkable element at room conditions. It crystallizes into a complex orthorhombic structure with mixed metallic covalent bonding, including these gallium-gallium dimers indicated by the yellow bonds. And this bonding gives rise to some unusual characteristics, including an enormously low melting point. So it will melt in your hand, and as this figure shows, also in your tea. So consequently, it's got one of the largest liquid stability ranges of any element, and also has an unusual 3% volume expansion on solidification. So the uses of some low melting point gallium-based liquid metals can have applications from cooling integrated electronics to manufacturing flexible and reconfigurable electronic devices. But interestingly, at high pressure, the melting curve of gallium is initially negative. So simply squeezing gallium in a high pressure cell will cause it to melt, until around 1.2 gigapascal, where the melting curve then becomes positive. But little's known about the structure and properties of liquid gallium at very high pressures, beyond a few GPa, primarily due to the experimental difficulties associated in accessing these extreme conditions. So very briefly, on just one slide, I'll give a brief introduction to the experimental work. So to determine the structure of gallium at high pressure, we used a diamond anvil cell. And here our samples compressed between the tips of two gem quality diamonds, which have the capacity to generate pressures routinely up to 100 gigapascals, which corresponds to conditions experienced deep in Earth's lower mantle, and beyond this even to reproduce conditions experienced in the Earth's core. The diamond anvil cell is heated within a vacuum vessel, shown here, installed at X-ray diffraction beamline at Diamond Light Source, where high flux X-ray or a high flux synchrotron X-ray beam is instant through the cell and scatters from the sample to measure its diffraction pattern and hence liquid structure. So in addition to these experimental measurements, I made ab initio molecular dynamics simulations of liquid gallium using the VASP code on Blue Crystal 4. So ab initio molecular dynamics computes the electronic forces on the atoms within a configuration box by solving the many-body time-independent Schrödinger wave equation. And this is extremely computationally expensive and scales with the number of electrons in the supercell. At each time step, the atomistic configuration is involved by classical Newtonian mechanics, but these forces are derived by quantum mechanical methods. So in my simulations, I used boxes of 600 gallium atoms in the MVT ensemble. So the number of atoms, volume, and temperature remains constant during each simulation. And then the structure was first melted at 6,000 Kelvin to ensure complete melting of the gallium, before cooling to target temperature and equilibrating for 15 picosecond with a time step of 1 femtosecond. So using 10 nodes on Blue Crystal 4, giving 280 CPUs, the calculations require 7 days per 5 picosecond interval. So they're quite computationally expensive. So here I show the experimental and simulation conditions explored. Experimentally, the melting curve was constrained by observing either the liquid diffuse pattern shown here on the top left, or the single crystal solid diffraction pattern on the bottom left. And the melting curve here shown in blue was fitted through the midpoints of these melting brackets shown by the blue diamonds. And then we made long 20-minute diffraction measurements every 2 to 3 gigapascals or so in the liquid field just above the melting curve. Then the pressure temperature conditions of the ab initio simulations, which I ran, are represented by these crosses, which I made up to 33 GPa and 1000 Kelvin. So the power of ab initio molecular dynamics is illustrated really by its ability to accurately reproduce experimental measurements. So here I show the measured total structure factors from the diffraction measurements in black, and to get up to 26 GPa, together with some representative ab initio results in blue at the similar conditions. And we can see that the simulations are in very good agreement with the experimental measurements and their pressure evolution. The pair distribution function or G of R functions give information shown here on the right hand side on the local structure, and this is obtained directly from the simulation box or experimentally via Fourier transform of this measured structure factor. So the wide range of conditions which I explored in the simulations allow for a Mie-Gruniesen-Debye thermal equation of state to be obtained, shown here by the colored curves at different temperatures. And this equation of state agrees well with the experimentally derived density within the limits of uncertainty. And I also show here on the right hand side the gallium-gallium coordination number for both the experiments and simulations, which show similar trends, where at ambient conditions the liquid coordination number is around 10, which is lower than the typical value of between 11 and 12 found in other liquid metals. But with increasing pressure and hence densification, our coordination number increases to a value approaching 12, which is consistent with a simple close packed structure. However, going on this average coordination number alone can be misleading, and so a more detailed structural analysis of the simulation trajectories was performed. So this analysis, this part of the project was mostly done by Francesco Turchi in physics, who I contacted after running the simulations to show him my data and see if he can apply the methods he typically uses for analyzing the structure of colloidal glasses on this liquid metal system. So 2 descriptors of local structure were employed. either Voronoi indices and or the topological cluster classification. So in Voronoi tessellation, we form polygonal cells around each atom where the edges of these cells are at the point of equidistance from the atom's nearest neighbors. And then the Voronoi index then corresponds to the number of faces with a specified number of edges. Alternatively, the topological cluster classification, the local structure is described by a predefined library or zoo of some 33 clusters, which represent the minimum energy motifs found in classical simulations. And this topological cluster classification was developed by Alex Malins and Paddy Royale here in Bristol. So just as an example of other methods used, recent studies of local structure of liquid gallium and other liquid metals at elevated pressure typically employ simplistic reverse Monte Carlo modeling methods. And this method finds a model of the atomistic structure by moving atoms randomly and then minimizing the difference from this model and some experimental data. However, by using our ab initio results for comparison, we find this naive RMC approach can be severely misleading. So this is illustrated in this figure showing the Voronoi indices and topological cluster classification results for the ab initio simulations and two RMC simulations, which have a starting seed either with an ordered configurational cell or a disordered configurational cell. We find that the ab initio and both RMC simulations give rise to different results, with the RMC simulations giving rise to structures reminiscent of their starting conditions. And this is particularly evident in the final converged RMC simulation boxes shown on the right hand side, if you can see that underneath our heads. And so here, particularly with using an ordered configuration, starting configuration cell, we see that the converged RMC still preserves a lattice-like structure. But remarkably, both these RMC simulations share almost identical pair distribution functions, and both have otherwise good convergence with the ab initio G of R. So this really illustrates the need to go beyond such a simplistic approach and use ab initio. So now, considering the ab initio trajectories just above the melting curve, this figure tracks how the topological cluster features change as we move from low to high pressures and temperatures. And so with increasing temperature and pressure, the abundance of larger motifs increases, where the five-fold symmetric partially icosahedra 10B unit and the crystalline 11F unit both stand out, as their abundance almost doubles from low to high pressure and temperature conditions. So in order to understand how far the structure can be considered to represent simple hard sphere structure with increasing pressure, for every ab initio data set, the optimal hard sphere diameter and volume fraction were refined to fit the ab initio G of R. And as perhaps expected, with increasing pressure and temperature, the hard sphere diameter reduces slightly, while the volume fraction increases quite significantly with greater compaction. So finally, by running further constant volume event-driven molecular dynamics simulations for these hard spheres, using 600 particles in a box to match the ab initio runs, we then defined a scoring function delta to illustrate the deviation of the ab initio model from this hard sphere structure. And this is shown here on the left figure by this contour map, where blue indicates the largest deviation from the hard sphere model through to orange and red contours representing the closest to hard sphere structure. So as indicated in our structural measurements, the liquid does indeed tend towards resembling a hard sphere structure at high pressures and temperatures towards the melting curve here. But there remains a large deviation of greater than 40% from this simple description over all pressure and temperature conditions. Interestingly, we find that the five-fold symmetric 10B and 12D motifs and the crystalline 11F unit, all of which are most prevalent close to the melting curve at high pressure, are also the units with the lowest configurational entropy, as represented by the figure shown on the right-hand side. And we postulate that the competition between these units, which have radically different geometry, may help to stabilize a metastable metallic glass structure in the supercooled liquid at high pressures. So in summary, we performed a combined in situ synchrotron X-ray diffraction and ab initio molecular dynamics study of liquid gallium to high pressure conditions. And the results reveal an evolution from a complex low coordinated liquid at low pressure towards increasing resemblance of a hard sphere structure at high pressures. But overall pressure and temperature conditions, the deviation from this simple hard sphere structure remains high, at least 40%. And above the high pressure melting curve, we observe the increasing prevalence of low configurational entropy motifs. And these have radical different geometries, and so may be important for stabilizing metastable metallic glass structures at high pressure. So thanks for your attention.
That's great, thank you, James. How fascinating. Who knew that gallium had such interesting properties? Really interesting. So while any questions line up, anyone would like to raise a hand, I just wanted to quickly ask, what were the codes that you're actually running to do this simulation? You mentioned some quantum mechanical as well as molecular dynamics.
So it was run on Blue Crystal 4. It was run on VASP, which is proprietary ab initio software. Yeah. And then we also RMC was the RMC and the hard sphere models were run on some open source software just on regular PCs.
Right. But VASP was the one that you're running on Blue Crystal as the parallel version, yeah? Yes, yeah. Very cool, good. Well, I don't know if there are any questions coming in.
We've got a question from James Womack.
Hi, can you hear me?
We can.
Yes.
Oh, cool. Thanks for the great talk. My question is about the use of ab initio MD. So I was wondering, what about this system makes it important to use ab initio MD rather than using classical MD, which would be a lot less expensive to run and you could run for longer timescales?
That's yes, but I mean the problem with that is I couldn't find reliable potentials to use the gallium. So
that is the problem. Yeah,
there's always the problem. Whereas with ab initio, you have a library of pseudo potentials, but then the electronic structure is calculated on the fly, so you don't need to worry about finding some potentials which someone else has already developed.
So if you could obtain well parameterized potentials for gallium, you would be interested in running classical MD.
Yeah, so I mean, often people use ab initio techniques to then to refine their empirical potentials. And so, yeah, it'll be useful to see actually what potentials are available and how the results compare to these ab initio calculations.
Mm.
But it would be useful because then you can extend the simulation cell and so gain access to larger range structures.
Mm-hmm. Okay, thanks very much.
Okay, thanks.
Thank you, James. Were there any more questions?
I had one question, Simon.
Go ahead.
You've been looking at gallium. I wonder if there are any other interesting metals or other elements you'd like to have a go at in a similar vein?
So there are several elemental liquids that have some strange properties, such as bismuth, or and actually we got a proposal at Diamond to look at liquid mercury. But actually gallium, experimentally, gallium was you think mercury would be good because it's already a liquid at ambient conditions, but actually the melting curve of mercury rises quite steeply. So we need to heat the sample at much higher temperatures. So it's more challenging experimentally, but we've got that proposal. And so that's the next system really that I'll be looking to run some simulations on as well. But yeah, there's several of these elements which have the low have a negative melting curve. So it's interesting to see what structures in the liquid may form that gives rise to that unusual behavior.
Great, thank you.
And thank you, James. So thank you very